Hey everyone, thank you so much for being here. Breaking into AWS accounts is a topic that's near and dear to my heart, and I'm sure for many of you as well. But I think if we're being honest with ourselves, the traditional methods for gaining access to AWS environments are boring. If we were to poll the audience for real-world breaches involving AWS environments, I guarantee 95% of scenarios will fall into one of three categories. They were either caused by a leaked access key, an exposed S3 bucket, or an exploited EC2 instance. These are the stereotypical ways that adversaries gain access to AWS environments. And to be clear, these are very real risks that we do have to contend with, but at the same time, they're remarkably boring. What we're going to be doing instead is taking a look at more novel approaches to gain access to AWS environments. We're going to be kicking in the door to the cloud by exploiting vulnerabilities in AWS services directly, particularly taking advantage of pre-existing trust. What I mean by that is a common design pattern within AWS is to have IAM roles in your account that have a trust relationship back to some AWS service. This enables that service to perform functionality and do things in your account. In this session, we're going to take a look at some vulnerabilities that would allow us to abuse that trust relationship and hijack that access to gain access to vulnerable AWS accounts, so that from there, we can escalate privileges, access resources, move laterally, and more. In this session, we'll talk a little bit about how this trust is established between IAM roles and AWS services, and then we'll dive deep on two vulnerabilities, as well as a more general misconfiguration that would allow us to take advantage of this. And finally, we'll talk about prevention options. In the absolute worst case scenario of an adversary having a cross-tenant zero-day in AWS, what options do we have to try and mitigate some of these attacks? It's important to note all of the vulnerabilities we're going to be talking about today have since been fixed by AWS. So think of this more from the perspective of what can we learn from these vulnerabilities that we can apply to better attack and defend cloud environments. With all that out of the way, to get us started on the topic of abusing pre-existing trust, we should probably talk a little bit about how that trust is established. In AWS, every IAM role is going to have a role trust policy. And this policy determines who or what is permitted to assume an IAM role. Where I think role trust policies are the most interesting are when they're tied to an AWS service. To demonstrate this, we're going to use Lambda as an example. What you see on the right side of this slide is the default out-of-the-box role trust policy associated with a role used by Lambda. If you were to create a function today, a role would be created for you that would have this trust policy. The way this works in practice is every time your Lambda function is executed, the Lambda service will assume that role in your account and do whatever it is that you want it to do. Now, this behavior is interesting when we start asking questions like, OK, since this is the default trust policy, and theoretically the overwhelming majority of roles using Lambda would have it, and since we already described that the trust policy determines who can assume a role, in this case allowing the Lambda service, could I do something like this? By creating a Lambda function in my own attacker-controlled account, but pointing to or referencing a role in a different AWS account, preferably one that I don't have legitimate access to. Could I cause the Lambda service to assume that role and perform API calls on my behalf? Well, the good news or bad news, depending on your perspective, is there is something that stops this, and that's called pass role. Anytime you are providing an IAM role to an AWS service so that it can be assumed, you are interacting with pass role. One of the core tenets of which is that you can only pass a role within the same AWS account. If you try to pass a role outside of it, you'll get the error message, access denied, cross-account pass role is not allowed. Now, this is a very important security boundary in AWS, because without it, we could just arbitrarily assume role into anybody else's account and access whatever resources are associated with those roles. So this will be our first goal of the session today, trying to find a way to bypass this filter and specify arbitrary IAM roles for a given AWS service. Because with this, we can move laterally into victim AWS accounts and access all the resources that they have access to. And so the first vulnerability we're going to be covering today is a confused deputy vulnerability in AWS AppSync. If you're not familiar with AppSync, AppSync is a managed GraphQL service offered by AWS. It allows you to quickly and easily build GraphQL APIs. The way that it works is very similar to what I described with Lambda. You first create an AppSync API in your account, you configure it, set your schema, and so on. And then as a part of setting your data source, a role will be created for you that by default will have a trust policy back to the AppSync service. Then, every time your function runs, the AppSync service will assume the role in your account and do whatever it's meant to do. And also similar to Lambda, if you try to pass a role outside of your account, you get the error message, cross-account pass role is not allowed. Now, you might be trying to think of some ways that we could bypass this control. Things like weird encoding schemes, maybe something like HTTP request smuggling, or perhaps something even more exotic. These are all great ideas, and I strongly encourage you to pursue them in your own time, but we actually found a much simpler way to bypass this control through the power of SpongeBob memes. See, under normal circumstances, the AWS API is typically case sensitive. What we mean by that is whenever you provide a parameter to the API, it expects it to be in a very particular casing. So long as you match that expectation, things work normally. So as a completely unrelated API, just to demonstrate this behavior, here we're performing the secrets manager create secret API call. And that expects a name parameter with a capital N. So long as you meet this expectation, you get a 200 OK, everything worked normally, you successfully created a secret. But if you were to change that casing in any way, in this case to all uppercase, and you try to send it to the API, you actually get an error. 400 bad request, member must not be null. The reason for this is, well, we didn't actually send the parameter it was looking for. It might have been the right alphabetical characters, but it's not the specific one, and it rightfully so returns an error. While this may seem like a somewhat obvious thing to point out, the reason this mattered is that by comparison, the AppSync API was an oddity. It was not case sensitive. We could pass arbitrary parameters of mixed case, and it would take it completely normally. Presumably, somewhere on the back end, it was normalizing these values in some way. Now, the parameter you would use to pass a role to the AppSync service was called service role ARN, capital R, capital A. If you try to pass a role outside of your account, well, again, cross-account pass role is not allowed. But if we change the casing of that parameter in any way, in this case, to all lowercase, and we passed a role outside of our AWS account, for some unknown reason, whatever filtering or checking that was supposed to occur either didn't happen or completely failed. And so with this method, we now had a way of assigning arbitrary IAM roles for the AppSync service to assume. So we were able to break a major security boundary in AWS through SpongeBob memes. With this capability, we could now offer arbitrary roles to the service and try to have it assume it. Put another way, any legitimate role that used the AppSync service in any AWS account was now a target for us to assume into and access whatever resources were associated with that role. This is an example of a cross-service confused deputy attack, where a lower privileged entity, in this case us, was able to trick or coerce a higher privileged entity, in this case the AppSync service, to do something on our behalf. And in this scenario, that was assuming a role in the victim account and carrying out whatever API operation we wanted it to perform. It's important to note, the thing that enabled this attack, the thing that made this all possible, was that pre-existing trust between that IAM role and the AppSync service. Because the role trusted the service, and because we weaponized the service against it, we now had an avenue to assume these roles. For a practical example of how we would exploit this step by step, we would first create an AppSync API from our own attacker-controlled account. We'd set the schema, configure it, and so on, determine what API call we wanted to make. We would then perform that pass role bypass to specify the role in the victim account that we wanted to assume. And then finally, we would run our API. Under normal circumstances, the AppSync service would assume the role in our account. But because of this vulnerability, it instead assumes the role in the victim account and carries out whatever API operation we want it to perform. And so that allows us to do things like you see in this screenshot, where we're actually dumping the contents of a DynamoDB table cross-tenant in AWS by having it perform the DynamoDB scan operation. If you'd like to learn more about this vulnerability AWS did release a security bulletin about it. And additionally, we have a blog post linked there with a ton of additional information on carrying out confused deputy attacks in AWS. Before we get to our second vulnerability of the day, we need to learn a little bit about assume role with web identity. Up until this point, we've been talking about plain assume role. And this is typically used for AWS to AWS role assumption. Now, while this is great, it does have a bit of a limitation. And that is that it requires the entity doing the role assumption to originate from AWS. And unfortunately, there's a variety of use cases in which you might want to have some identity be able to assume a role from outside the cloud. How do you deal with this? Well, that's where assume role with web identity comes in. The sort of core premise here is that you offload the responsibility of authorizing that role assumption to an identity provider of your choosing. This can be a private identity provider, one that you or your organization own and maintain, or it can be a public identity provider. Think things like Facebook, Google, Amazon, GitHub, and so on. The external identities, whether they be human or machine, will interact with that identity provider, generate a token, and then use that to authenticate in the assume role with web identity call to assume that role in your account. Now, before we get to this next part, I really have to stress that this is a general design pattern. A variety of services will use it, including some that are native to AWS and some that are completely unrelated. We're going to be taking a look at GitHub Actions, which is a common use case for this type of thing. But again, really want to stress that there are a variety of services and technologies that will do the very same thing. Now, like I mentioned before, every IAM role has a role trust policy. What you see here on the slide is the most basic, bare bones, simple trust policy you could have had to be usable by the GitHub Actions service. And what this trust policy says is that we're going to allow the GitHub Action identity provider the ability to assume role and web identity in this role in our account. And if we think about that, that's a bit of a terrifying thought. Because what that policy does is it just trusts the identity provider. And if we think about it, that identity provider is public. It's global. There's nothing stopping an adversary from creating their own GitHub account, creating their own GitHub action to generate a token signed by that very same identity provider and using that in the assume role with web identity call and being able to assume that role in your account. That is why anytime you use assume role with web identity with an identity provider that is public or global in a sense, you need to have a condition which restricts who specifically is permitted to assume that role. Again, assume role with web identity is a general design pattern. The specific condition that you need will depend on the scenario. To continue using GitHub Actions as an example, you need to restrict which GitHub organization or which GitHub repo is allowed to assume the role. Now, the attack I just described was very much in vogue last year. A number of security researchers, including my own colleague Christoph, identified this potential misconfiguration and sounded the alarm about it. If you'd like to learn more, we have a blog post with a ton of additional details. Now, to AWS's credit, they actually did something about it. In response to this increased awareness, they actually made changes to IAM so that you can no longer create a vulnerable policy like this one. If you try to, you'll actually get an error and it will reject it. They made a once optional condition now mandatory. Now, this is great, fantastic. Really appreciate that, AWS. But if we were to nitpick it, it's really important to stress that they only did this for the GitHub identity provider. Any of the other services that are similarly impacted were/are still vulnerable. And for this reason, if you're a heavy AWS user, I strongly encourage you to audit your IAM roles that use assume role with web identity and look for this misconfiguration. Because if it's present, anybody could just assume your roles. Now, speaking of services that were similarly impacted, I wanted to take a look at Amazon Cognito. If you're not familiar, Amazon Cognito is a sign-in as a service offering from AWS. If you want to store user credentials, but you don't want to deal with the hassle of hashing, salting, password reset flows, and so on, you can pay Amazon a fee, and they'll take care of that for you. One of the core features of Cognito is something called an identity pool. And an identity pool is a resource you can create in your account that allows you to distribute short-lived IAM credentials to your users. So for example, say you're building a web application and you want your users to be able to upload content to S3 or perhaps invoke an API gateway using IAM auth, the way you could achieve this is by creating a Cognito identity pool in your account. Your users will interact with it and authenticate so that they can then assume the role in your account. Now, the good news when it comes to Cognito is that out of the box, they seem to have considered this very same attack I just described with GitHub Actions. Specifically, by default, there is a condition which restricts which identity pool is permitted to assume a role. And this would effectively mitigate the attack. However, if that condition wasn't present, and we're going to be talking about some reasons why it wasn't present in just a little bit, anyone in the world would be able to assume this role. The specific way that they would do it is by creating their own Cognito identity pool in their own attacker-controlled account. By authenticating it, or by interacting with that, they could get that token and pass that into the assume role with web identity call. So for our purposes today, we will refer to this as the variant 1 vulnerable policy, a policy that trusts Cognito service but doesn't limit which specific identity pool is permitted to assume it. The reason we're referring to this as variant 1 is because there's a variant 2 as well. You might have noticed when I showed the default trust policy, there's actually 2 conditions. This second one is the AMR condition, or the authentication methods references. And you might wonder, could we assume a role that had this condition set? And it turns out we absolutely could. All this condition is doing is checking that you are authenticated to an identity pool, not that you are authenticated to a specific identity pool. And because we can just create our own identity pool, we can configure it however we like, and so we can set up that authentication piece to satisfy this condition. So for our purposes today, we're going to refer to this as the variant 2 vulnerable policy. Now, you might have noticed I refer to these as misconfigurations, and that's because they are. Everything we've talked about so far when it comes to assume role with web identity has been a misconfiguration. The GitHub Action stuff, Cognito stuff, any of the other technologies and services that have this very same issue, they're all misconfigs. And so at this point, you're probably wondering, well, Nick, I was promised a second vulnerability. You're telling me this is a misconfiguration. What gives? Well, this is where things get weird, and we dive into the second vulnerability, the AWS Amplify service exposing IAM roles to take over. See, earlier this year, when we noticed this potential misconfiguration in Cognito, one of the first questions we had was, OK, cool. I wonder how common this misconfiguration is. And because it can be used for initial access, literally just like assume rolling into victim accounts, we wanted to know if we could use publicly available data to find vulnerable roles and notify their owners so that they could be fixed. To do this, we used a tool called SourceGraph, one of the free features of which is essentially a Google search, but for public GitHub repos. We wrote a regular expression to find IAM role ARNs, threw that into SourceGraph, got back results, deduplicated them, removed like clearly placeholder ARNs and so on, and that left us with a little over 8,000 results. From there, we then tried to assume each role twice, once authenticated, once unauthenticated. We let our automation run, and pretty much immediately it was clear that something was terribly wrong. Remember, this was across basically all of public GitHub, across teams, organizations, individuals, and companies. So why was it then that the overwhelming majority of roles that we found to be vulnerable all had this weirdly specific naming convention? What you see here on the slide are a handful of real roles that we found in the wild that were vulnerable that we've slightly modified the names of so as to respect the anonymity of their owners. Now, what made these roles so strange was that they all ended in either auth role or unauth role. And additionally, they had timestamps dating back to either 2018 or 2019, or they would have a 6-digit integer. Presumably, these were the newer ones. To make things even more strange, we actually found 3 roles that were vulnerable that belonged to AWS themselves. And so at this point, it wasn't clear what was going on. Was this some sort of tutorial or demo gone wrong where somebody was demonstrating how to do this but didn't realize it was vulnerable? Using SourceGraph, we were able to see the names of the files where the majority of these roles were being found. And again, the overwhelming majority were found in a file called teamproviderinfo.json. And this ultimately led us to the culprit who was causing these roles to be vulnerable. It was AWS Amplify. Normally, when we're talking about a misconfiguration in the cloud, we're talking about mistakes, misunderstanding, developers moving a little bit too quickly and breaking something, or not realizing that something is as exposed as it actually is. This is a rare circumstance in which an AWS service itself was exposing IAM roles such that anyone in the world would be able to assume them. And unfortunately, they didn't just do it once, they actually did it twice. If you're not familiar with Amplify, the sort of core idea behind it is that it's a framework for building web and mobile applications. By using Amplify, your developers can focus on writing code, and Amplify will abstract away a lot of the underlying infrastructure. So for example, if you want to build a web application and allow your users to be able to create accounts, sign up, change their passwords, and so on, your developers don't even need to know what Cognito is. They can simply add authentication, and Amplify will go in, create those Cognito resources, configure them, and so on. Key emphasis, Amplify configures those Cognito resources. Now, one challenge we often have as cloud security researchers is that it's not clear why certain vulnerable behaviors are introduced. If we compare this to the first vulnerability we found today, for some remarkably strange reason, changing the casing on a JSON parameter let us break a major security boundary in AWS. So you run into these scenarios where it's clearly not good behavior, but you're not sure why it's occurring. The Amplify vulnerability is actually one of the rare circumstances in which we're able to know definitively not only how this was introduced, but when. And that's because the Amplify CLI, written by AWS, is actually open source. And by digging through the commit history, we can see how and when these vulnerabilities were introduced. And that's how I can tell you that on or around July 3rd, 2018, the variant 2 vulnerable trust policy was introduced to both the Amplify CLI and the Studio. What was happening was anytime you created an Amplify project, two roles would be created by default in your account, an auth role and unauth role like we saw previously. Unfortunately, as a part of this commit, the default trust policy for these roles out of the box was the variant 2 vulnerable policy. Simply creating an Amplify project, using the service completely normally as you would expect, would introduce two roles in your account that could be assumed by anyone. So if you thought you were building a private, internal-only application that you were requiring authentication for and gatekeeping who could create accounts so that you could protect whatever resources were associated with them, well, unfortunately, no, you weren't. Anybody could have just assumed those roles in your account and accessed any resources associated with them. Like I said, that was introduced on July 3rd, 2018. A little over a year later, on August 8th, 2019, AWS seemingly unintentionally fixed this behavior. In particular, they set the new default effect on that trust policy to deny, and they removed the condition entirely. And this is actually the same default trust policy that you would see today if you were to create an Amplify project. Now, it's really important to stress that when we say fixed, what we mean by that is that no future roles would become misconfigured. Any that had already been created were still vulnerable and could be assumed by an external adversary. That's how we were able to assume them in 2024. Next, on July 22nd, 2020, the variant 1 was introduced to the Amplify CLI in Studio. And this one was a bit more complicated than the previous one. Like I said before, you can add authentication to Amplify projects. If at any time you chose to remove that authentication component for any reason, that would introduce the variant 1 vulnerable trust policy. In speaking to developers who were impacted by this issue, it seems the most common reasoning for this to occur was situations where an Amplify project started with the built-in Cognito resources, and then at a later time moved to Cognito outside of Amplify, or to just a different identity provider entirely. Regardless of your reason why, what occurred was that a CloudFormation template would run that would originally set the trust policy to what you see here on the slide, which is totally fine. This is the secure policy. However, under the condition for the deletion of the authentication resources, there was a line to delete the condition off of the trust policy. And when that happened, all that you were left with was the variant 1 vulnerable policy, allowing anyone in the world the ability to assume that role. Crucially, when this exposure occurred, whatever identity policies were associated with your role, it still had access to. And additionally, unfortunately, developers love to overprivilege their identities. When we were reacting to this vulnerability and notifying customers so it could be mitigated, we found a number of customers who had highly privileged IAM roles, including some with S3 full access, Kinesis full access, and more. Unfortunately, as a part of this vulnerability introduced by Amplify, now anybody else would have those very same level of privileges in their account. So like I said, that was introduced in July of 2020. We eventually identified this and disclosed to AWS on January 9th of 2024. In response, AWS has fixed this issue, and in particular, they've gone a little bit above and beyond what they did with GitHub Actions. They did the same thing where you can no longer create a vulnerable trust policy in this way, so variant 1 or variant 2 can't make it anymore. However, they also made changes to STS itself, so that even if there was a vulnerable role, an external account can no longer assume that role in your account. If you'd like to learn more about this vulnerability, AWS did release a security bulletin for it. And additionally, we have a blog post with a ton of additional details on how we found this issue and other similar types of attacks you can do in AWS. With the time we have left, I wanted to talk a little bit about what we can do to prevent cross-tenant attacks. To be clear, your time is probably much better spent doing things like deleting IAM users, cleaning up old access keys, following least privilege, and so on. But if you're already doing all that, or you have the technology and processes in place, this might be something that you consider. One of the neat tools that AWS provides us are a number of condition keys that can restrict where an attacker can be coming from, sort of similar to what we saw with the assume role with web identity conditions earlier. These allow you to restrict what ARM, what account, or what AWS organization is permitted to assume a particular role. To be clear, these are not included by default when you create a trust policy. You would have to manually attach these to each role, and more importantly, make sure that the service that you're using is compatible with these condition keys. From some nominal testing, it appears that EC2, Lambda, and AppSync all work totally fine. But again, strongly encourage you to test this before you push it into production. As an example of how this can protect your roles, we'll use source account as an example alongside the first vulnerability we talked about today, a confused deputy vuln in AWS AppSync. With this particular attack, an adversary would be able to weaponize the AppSync service to assume a role in a victim account. However, if we added a condition on that trust policy to restrict what account is permitted to assume it, we can actually successfully block an external adversary. And the reason we know this is, back when that vulnerability was still present, we were able to test this for ourselves and see that by setting this condition, we could successfully block an adversary. So even in that worst case scenario of somebody weaponizing an AWS service against customers, you could actually defend your organization from that type of attack. Additionally, another reason I like this is it's a form of defense in depth. If past role states, under no circumstance should someone be able to assume a role cross-tenant in AWS, great. We beat that with SpongeBob memes. So the next time someone gets around that, let's have an additional layer of defense to block this type of activity. So in conclusion, we took a look today at how confused deputy attacks can weaponize cloud services against us. We took a look at assume role with web identity and a very important misconfiguration that could lead your roles to be vulnerable. Again, if you're a heavy AWS user, I strongly encourage you to audit your roles looking for this type of misconfiguration. It's an easy one to make. So easy, in fact, AWS actually made it twice. Additionally, we took a look at how condition statements and condition keys can potentially defend us from confused deputy attacks in AWS. If you enjoyed this talk, you can find more of our research at securitylabs.datadoghq.com. My name's Nick Frechette. If you have any questions, feel free to follow me to the wrap-up room, or feel free to reach out over social media. Thank you all so much.